Hello, everyone. My name is Ryan Jones, and along with Dr. Brendan J. Gifford, our project is called Assessing Radiological Sample Composition Using Laser-Induced Breakdown Spectroscopy and Machine Learning. Laser-Induced Breakdown Spectroscopy, otherwise known as LIBS, is a portable technique that generates an elemental fingerprint of materials. Spectroscopy being the study of the absorption and emission of light and other radiation by matter. This technique uses a high-power laser that turns micrograms of surface material into a plasma, the emission of which can be detected and used to determine the concentration of major and trace elements in solid, liquid, or air samples. Its purpose is to be able to detect and characterize materials. There are other techniques that could have been utilized, but they are much bigger than the handheld spectrometer, like shown in the image. And so using the spectrometer allows us to bring the instrument to the sample using LIBS in order to keep the samples in the original place and not move them to a special medium. In this case, our samples are very heavy metals called acetonide. The emitted light is collected and coupled with the spectrometer for LIBS spectral analysis. And then each element on the periodic table is associated with a unique LIBS signature or spectral peak. By identifying the different signatures for the analyzed samples, its chemical composition can be determined. Therefore, LIBS can be effective for material analysis over a wide range of sample matrices. In this project, a neural network was created based off LIBS. A neural network is a computer architecture that processes data in a similar way to a brain. It uses neurons in a layered structure that resembles the brain. It does this through machine learning. The inputs in the neural network are the spectra, which are a continuum of color formed when a beam of white light is dispersed so that its component wavelengths are arranged in order. And our outputs are the compositions of the sample. Machine learning uses the complex structure of the hidden layer to represent any possible function or feature to be learned and used as input for the next layer. Hidden layers allow neural networks to be more detailed. For example, if you were growing a tree and you wanted to calculate how tall can it possibly grow, you would take multiple things into factor, such as how much water you give it, or sunlight, and the type of soil it grows in. The hidden layer would include many more features that relate or affect growth even in the slightest, such as humidity, moisture, etc. Making the network as intricate and detailed as possible allows the network to recognize the many relationships between vast amounts of data and come up with the best output possible. And this is all possible due to machine learning. So you may be asking yourself, what exactly is machine learning? Machine learning is defined as a type of artificial intelligence, or AI, that allows software applications to become more accurate at predicting outcomes without being explicitly programmed to do so. It recognizes complex relationships and figures out the relationship between inputs and outputs. It is great for allowing a user to have a large amount of data into the algorithm and have the computer analyze it, learn from the data, and improve the accuracy of outputs using automated optimization methods. Machine learning algorithms use historical data as inputs to predict new output values. The machine is taught by example in this case. It is provided a known data set that includes desired inputs and the outputs, and the algorithm must find a method to arrive at the desired output. It identifies patterns in data, learns from observations, and makes predictions. This type of method is great for achieving a high level of accuracy. Coding is an important part of machine learning and is part of the testing and evaluation of the machine learning models. Machine learning is implemented through some coding language, which in this case is Python. Python is the most used programming language for machine learning and development. 57% of data scientists and machine learning developers use it, and 33% prioritize it for development. My contributions toward the study are that I developed the software package for the spectroscopists that will allow them to import their data and make predictions. The purpose was to produce an easy-to-use software program that rapidly and efficiently interprets LIBS spectra from the acetonide samples and outputs the composition to the user in an elegant way. This included using 3 programs throughout the project, the first being Anaconda, second Visual Studio, and lastly, Jupyter Notebook. These 3 programs were used throughout the project, and then we have Miniconda, which is a different version of Anaconda. So Miniconda allows the users to create separate environments for each of their projects and to install only the packages that you need for them. Jupyter Notebook is used for creating and sharing computational documents. I was given documents and data from Jupyter Notebook and imbued it into Visual Studio, which is a code editor that is used for coding, debugging, and task running. Within Visual Studio, I used Python to write a script that will create a graphical user interface, otherwise known as GUI, which is a visual way of interacting with a computer using items such as windows, icons, and menus. I also use tkinter as my GUI library, which basically allows the programmer to produce GUI code for multiple computer platforms. This is important because we want to have a cross-platform so the same code works from one computer to another type of computer, whether one person has a MacBook or another person has a Windows laptop. Creating a single application that runs the same on several platforms makes compiling code much faster and easier. In the GUI, I used an open file dialog to display a standard dialog box that prompts the user to open a file. The user will only be able to open CSV files, which is then converted into a text array. Once this happens, the array will be displayed in a dialog box. And I'm currently trying to make it to where only the predictions will be displayed. As for our current results, I have been able to create a slider widget that moves from left to right, or from 0 to 172. It got the last number 172 from taking the length of an array of integers imbued in the code editor. A demo button, in this case, the prediction button, was created so that when a slider scrolls to any number from the range, once clicked, the button will cause the current value numbers to print out a value correlating to the number the slider is on. The GUI also displays a dialog box that prints out a list of numbers from a CSV file that the user inputs into the GUI by pressing the button Open a File. The user is able to press the Open a File button and select a CSV file from their file explorer. Once they select one, the GUI will display the second column of data from it. In this case, the CSV file being selected in this project is data from a libs file, and the predictions of the input will be displayed. Some key takeaways I received from this project are that libs is a great spectroscopy technique that can be used in a wide range of environments due to its versatility. It can be used on any material, whether if it's solid, liquid, or gas, and it can detect chemical elements. I also learned about the amazing power of machine learning and how it can truly increase the speed at which data is processed and analyzed and be applied to many different things. It created high-value predictions based on input data. As for the future findings, I would like to be able to adjust the software program so that the GUI prints out a singular accurate output when given an immense amount of data as the input. I would also like to clean up the coding a bit to make it more efficient and focus on removing any bugs that may be in the program. I'd like to sincerely convey my appreciation and gratitude to my school, Harris-Stowe State University, for providing me the education and study to be able to be well-grounded in the skills required for this program. I would also like to thank Texas A&M University for giving me the opportunity to be a part of this extensive study, which allowed me to learn a lot of new topics. And Los Alamos National Laboratory for sponsoring the program. I also thank my mentor, Dr. Brendan Gifford, for teaching me and supporting me throughout the entire program. I truly learned a lot from him. Thank you to everyone who has helped me, and have a great rest of your day.